Today, we're continuing with a series of talks on complex multiplication and reduction of curves and abelian varieties. And I'm very happy to introduce Wanlin Li, who is speaking to us on a generalization of Elke's theorem on infinitely many supersingular primes. And Wanlin, is it all right if we video this talk?
Yes, that's all right.
Oh, great. Well, please continue.
Okay, thanks for the invitation and thanks for coming. It is my great pleasure to talk about my ongoing work joined with Elena Mantovan, Rachel Price, and Yunqing Tang on generalizing Elke's theorem on infinitely many supersingular primes. So also I want to thank Norm Elkis for his beautiful talk from 2 weeks ago. And let's first recall what some of the results he discussed in his talk. So in 1987, Elkis proved that if you take any elliptic curve defined over Q, then there exist infinitely many primes at which the reduction of E is supersingular. So this is a difficult result. One reason is that if your elliptic curve E does not have complex multiplication, then Serre proved that at 100% of the primes, the reduction of E will be ordinary. So the theorem of Elkis is really proving that a density zero set of primes being infinite. And moreover, heuristically, we expect that the number of supersingular primes for a non-CM curve is of size x to the half. So moreover, later on, Elkis generalized his theorem to a large set of number fields, including number fields which admits one real embedding. And there are some other totally complex fields that he could also handle. And later on, after his theorem was out, there were some generalizations to certain abelian surfaces with quaternatic multiplication. These were obtained by the work of Jiao, Sandorf, and Baba-Gronans. So all of these abelian surfaces lie in some families which are parametrized by some genus zero Shimura curve defined over Q. And beyond abelian surfaces, there aren't many results known. So today, I want to present our ongoing work. This is a showcase of a theorem that we could prove. So we consider a family of genus 4 curves, so which has a affine model defined by y to the 5 equals to x times x minus 1 times x minus t. So this family is a family of genus 4 curves. Okay, taking any smooth curve in this family, and we require two local conditions. One local condition is at the Archimedean place. We ask a rational function, which in terms of t, which we will call the generalized J invariant. We ask this value for C to be in Q, and it's between the range 0 and 27 over 4. Moreover, we ask the reduction of C at the prime 5 to be singular. So as I already explained, this is the family of genus 4 curves. In this family, when you vary t, there is one singular fiber in this family, which is given by two copies of a genus 2 curve and intersecting at a node. Okay, and this is the only singular fiber. We ask the reduction of CF5 is having this model. Then we could prove that there exist infinitely many primes at which the reduction of the Jacobian C to be quote-unquote supersingular. Here, by supersingular, we mean that if you consider the p-divisible group over a p-bar, then depending on p, it is isogenous to two copies of the p-divisible group for ordinary elliptic curve, direct sum two copies for the supersingular elliptic curve. If p is 1 mod 5, we would say that's supersingular if p is 1 mod 5. And if p is 2, 3, or 4 mod 5, then by supersingular, we mean that the reduction of Jacobian C at P actually is indeed isogenous to 4 copies of the supersingularity curve. And this is the analogous notion at supersingularity for elliptic curve, which I'll explain now. Okay, so the point is that in general, if you are given an abelian variety A defined over a P bar, and consider the isogeny class of the p-divisible group, then it is determined by a discrete invariant called Newton polygon. The Newton polygon for Jacobians of curves over a defined over positive characteristic field is actually an area with lots of interest that I unfortunately don't have time to discuss today. But if you're interested, I highly recommend a survey paper written by Rachel Priest called Current Results on Newton Polygons for Curves. That's a very nicely written survey and describes this very interesting area. But here we can just think about the Jacobians for our family. So in general, if you consider Newton polygons, which arise as for G-dimensional abelian variety, then it has a pole-set structure. And in particular, this partial ordering gives a stratification on the moduli space of principally polarized abelian variety of dimension G. And in this stratification, there is the largest locus, which is the ordinary locus, and the smallest locus is the supersingular locus. So for example, if we consider the modular curve case, if I consider the curves x01 over fp bar, then we know that for this is a J line, right? This is a J invariant parameterizing isomorphism classicity curves over fp bar. Then we know that for almost all the J invariants, for open dense set of J invariants, the curve is ordinary. And there are finitely many J invariants corresponds to supersingular curves. And this is exactly this Newton stratification in this dimension 1 case. And in general, the number of Newton polygon or the number of the number of Newton strata is actually quadratic. Is quadratic in G. Okay, so there are many more Newton stratas when the dimension of the variety gets higher. So now let's consider this one-dimensional family of curves we look at, and consider T, consider parameter T inside taking value inside fp bar. Then really I'm thinking about my family of curves as in some sense A1 parameterized by T, right? Then I can consider the Torelli map, which is given by taking a curving map family, and the map is Jacobian. Then the Torelli map takes my family of curves now to A4 fp bar, right? And then I can think about which Newton strata inside A4 intersects my Torelli image. And for this particular family, actually for each phase P, as long as P is not 5, there are exactly 2 Newton stratas. And one of them is open, one of them is open and dense, called mu ordinary, and the other one consists of finite many points. This is our quote-unquote supersingular locus that we're talking about. As you can see, when you look at my family over P bar, the notion of supersingular here is really very similar as the notion for supersingular elliptic curves. And also the fact that there are only 2 possible Newton polygons showing up for this family is actually something special. If you in general take a one-dimensional family of curves and look at over P bar and look at the Newton locus, you'll see that you wouldn't just get 2 locus in general. Okay, so this is explanation of what we mean by supersingular and why our result is analogous to LK's result. And later on, I'll explain why for our family, actually there are only 2 Newton locus. So here's another similarity, which is that recall in the very beginning of in the first slide, I mentioned that if you take a non-CMDT curve over Q, then at 100% of rational primes, its reduction is ordinary. Actually, in one of the joint work with Victoria Kantorov-Fafan, Alina Mantovan, Rachel Priest, and Ying Tang, we are also working on proving that for the family we are looking at 100% rational primes, our reduction will also be mu ordinary. So our result is also proving that a 0 density set of primes being infinite. Okay. And another remark I want to make is that we can actually naturally extend our theorem to, so in the very beginning, I asked J of C to be in Q, and we actually can extend it to Q joint square root 5. You can think now at this point you can think about J of C as in some sense a defining field of my curve, and I'll explain next slide what this really means. But here we actually the field we naturally work with instead of Q is really Q joint square root 5. So Q joint square root 5 for us is similar to Q for the elliptic curve case. But for the simplicity of the result and the presentation, I will restrict to Q. And but actually, we could work with Q joint square root 5. And another remark I want to make is, as I already mentioned, this is ongoing. What does a mu in mu ordinary mean? Oh, actually, I don't know. That's a notion that people use. I don't know I don't know the history of why it is called mu ordinary. Yeah, thanks for the question. Yeah, so the last remark I want to make is, as I mentioned, this is still ongoing work. So we are also currently working on extending the theorem I showed you to more curves in this family, meaning that relaxing our restriction on J and relaxing the reduction of C at phi being singular. And more also, we are working on generalizing our theorem to some other families of superlative curves. For example, one family we will consider is a family defined by vector 7 is equals to x times x minus 1 times x minus t. Okay, so after these remarks, let's talk about my family, which will give you a better understanding of our theorem. Well, I already mentioned that my family, when you first see this family curves, right? First of all, you can parameterize the curves in this family by the variable t, right? But this variable t, it is not in one-to-one correspondence to the isomorphism class of curves in this family. Actually, this variable t is more like the lambda invariant for the Legendre family. So when I consider this curve and consider the Legendre equation given by y squared equals to x times x minus 1 times x minus lambda, we know that lambda, there's a map from lambda to j, where j invariant, of course, determines isomorphism class with the curve. There's a 6 by 1 map, and 6 to 1 map. And we have this is also true for our family. So this generalized j invariant, which is the rational function in T we defined, actually uniquely determines its one-to-one correspondence to the isomorphism class of for objects in our family. But here, by isomorphism class, it means that not only the isomorphism class of the curve itself, it also together with the mu5 action. Okay. So this generalized J invariant will be a parameter for the coarse moduli space of our family of curves, which I will denote as S. S will be my coarse moduli space for this family. And as you can see, this is isomorphic to P1 over Q. Again, very similar to the modular curve case. And in the theorem, the first condition I asked was for J of C to be in Q. So this means that I ask the further moduli for my curve C is actually Q. Okay. So this is about the moduli space over Q. And now let's talk about the geometry of my moduli space over the complex numbers. So we've already seen that my family is actually in something special, right? Because it is given as a superlative curve. So over Q adjoint zeta 5, where zeta 5 is a fifth root unity, then my curve C actually admits an automorphism given by mapping each point x comma y to x comma zeta 5 times y. Then this automorphism gives rise to an endomorphism for the Jacobian of my curve. Then when I consider the Torelli map from mapping my curve to Jacobian, actually the image of the Torelli map of my family S naturally lies in a PEL type Shimura variety. And in this particular case, what we get actually is a compact Shimura curve. And this is a compact Shimura curve with reflex field being Q adjoint zeta 5. So which means that from the series of Shimura varieties, naturally this Shimura curve should be defined over Q adjoint zeta 5. But from the moduli perspective, which we discussed in the previous page, we actually saw that our S has a model defined over the rational numbers over Q. And this is actually one important fact for our work. So moreover, if I consider cyclic covers of P1 or mu m covers of P1 and ask is the moduli space of my family to be one thing to note is that my family is one-dimensional, and then it is embedded into a Shimura curve, which is also one-dimensional. So this means that my S actually agrees with the connected component with this Shimura curve. And in this particular case, actually this Shimura curve has only one connected component. So my S actually in this case agrees with this Shimura curve. But in general, If you consider one-dimensional if you consider C covers a P1 ramifies at 4 points, which is parameterized by P1, and ask is to be embedded in a one-dimensional Shimura variety, then Moonen gave a complete list of 14 such families. And these are the families that we are working towards generalizing our theorem to. So for example, the one that I mentioned, y to the 7th equals to x times x minus 1 times x minus t is one of them. So this is what I mean by we are trying to generalize our theorem. Okay, so now I know that my S is essentially agrees with a Shimura curve, PL type Shimura curve. Then I can start its complex structure. So for this case, the unitary symmetric domain for my Shimura curve actually is the upper half plane. So this means that if I consider over C, the complex points of my S actually is given by the upper half plane modular Fuchsian group. Again, very similar to the modular curve case, right? But instead of PSL to Z, what we have here actually is a triangle group. Is this a triangle group with index 2, 3, and 10? Which means that the fundamental domain for our curve is 2 copies of a hyperbolic triangle. So imagine this triangle, 2 copies of the triangle with their sides identified. This gives me a sphere, which is my P1 over C, right? Okay, so and the vertices of these triangles corresponds to curves in my family with extra automorphism. So every curve in my family has the automorphism given by zeta 5. But there are 3 special curves in this family has extra automorphism. And this gives me the vertex of the triangle. So let me just talk about these 3 points. So my point P, which corresponds to a J invariant being infinity, this is the singular point. Meaning that this corresponds to the curve that is 2 copies of a genus 2 curve intersecting at a node. But one thing to note that even though this curve is singular, its generalized Jacobian actually is abelian variety instead of a semi-abelian variety. So it's the direct sum of Jacobians of these 2 genus 2 curves. That's why my Shimura curve is compact. We don't have a cusp. That's one big difference from our case to the modular curve case. And then I have a point Q, which corresponds to J invariant being 0. And here, if I look at the automorphism of the curve corresponding to my Q point, it has automorphism Z mod 15Z. So apart from the zeta 5 automorphism, it has an extra automorphism order 3. And then I have an R point, which if you look at its automorphism, then the curve corresponding to the R point has an extra automorphism of order 2. And it corresponds to J invariant 27 over 4. So in my theorem, I ask the J invariant for my curve C that I work with to be between 0 and 27 over 4. That means that I'm really thinking about I need my curve to be lying between Q and R on this geodesic. These 3 geodesics, the size of my triangles, actually are the real points for my moduli space. So I'm considering a curve C whose point moduli lies on the geodesic between this point Q and this point R. Okay. Okay, so now we have talked about geometry of my moduli space over C. And we have mentioned that actually my moduli space agrees with the Shimura curve. Now we are ready to look at my moduli space over FP bar and discuss its Newton locus. And this explains why there were 2 Newton locus for my family. So for any P that's not equal to 5, the Shimura curve has good reduction at P. Then from the work of Wiener and Wedholm, on the Newton locus on Newton strata of PL type Shimura curves, we know that such a Shimura curve has exactly 2 Newton strata, and one of them is mu ordinary and one of them is basic. And the mu ordinary one will be open and dense, and the supersingular or basic one will be 0-dimensional, consisting of finitely many points. Actually, this is the fact that our moduli space agrees with the Shimura curve is why we know that for my family, I have 2 Newton strata. One of them is open dense, and the other one consists of finitely many points. And this is how we computed the given Newton strata. And then there's a one special case, which is that when P is 5, then the Shimura curve has band reduction there. And in this case, we don't get 2 Newton strata. Actually, there is a unique Newton locus for S over P F5 bar, and it is actually supersingular in the sense of the classical sense. So 5 is a very special prime for our family. Okay, so after so this actually is related to the fact that in our theorem, we ask the reduction at 5 to be singular. It's related to the fact that our family at 5 has only 1 Newton locus. Okay, so now I have explained the conditions in my theorem, the fact that what is the variable, or what is the invariant J of C, and what it means for it to be in Q, and what it means for it to be between 0 and 27 over 4. And also, we looked at the geometry of my family at 5. And also we explained what is the supersingular locus looks like for our family over P bar. So now let's move on to talk about proof. So my strategy of talking about the proof of theorem is that, first of all, I will throw away all the details, all the mathematical details, and give you a very simple strategy, a skeleton of the proof. And then I will add back in some details and give you a sketch of the proof. And then I will add in more detail to some steps that shows up in the sketch. Okay, so let's start with the version with no details at all. So when all the details are thrown away, actually this would be the same strategy as Alpy's proof. Okay, so the way I think about it is that I have a curve C in my family that is defined over Q in some sense, and I want to look for some primes where C admits supersingular reduction at. So the way I view it is that imagine you have an ocean full of primes, and this is a fishing game, and I want to catch some primes that satisfies a certain condition, okay? And I will call this set of primes, this set of desired primes T. Okay, since it's a fishing game, well, I'm going to build some fishing nets, and then each fishing net will catch me some primes, okay? So what are my fishing nets? Well, I will be constructing certain curves, a list of curves, C1, C2, and this will be my fishing nets. And then each Ci will catch me some primes. Which primes will it catch are exactly the primes such that if I reduce Ci and C modulo P, they are isomorphic. So, so this is really considering the arithmetic intersection of the curve C and Ci. But now let's just consider this as my fishing net catch me some primes, right? So now I want to catch a certain set of primes. So to do that, when I build my fishing nets, I give 3 conditions. So first of all, for each I we build Ci in such a way that for each I, Ti intersect my desired set is non-empty, meaning that each fishing net will catch me at least 1 prime that is of a desired type, right? And then, so I have infinitely many fishing nets. Each one of them will catch me at least 1 desired prime. In order to guarantee I got infinitely many desired prime, I just need to make sure that they are not catching the same prime again and again, okay? So the second condition is that if I have any P that is caught by 2 nets, is both in Ti and Tj, then it could only happen when P is not my desired type, meaning that if I consider C, the reduction of C at P, it is not supersingular. Okay, then this means that even though my fishing nets can catch the same prime, but the desired prime, each one of them can't overlap. But this condition only makes sense, only work if P is not 5, because we've already discussed that at prime 5, I have only 1 Newton locus. So it doesn't make sense to ask C mod 5 to be not supersingular. So that's why we add the third condition, which is that when I construct my curve Ci, I ask its reduction at 5 to be smooth. But remember that the reduction of C at 5 is singular. That's one of the restrictions on C we put in the very beginning. So this tells me that 5 is not in Ti for any I. Okay. And this actually would produce me infinite many desired primes, right? But the point is I built infinite many curves Ci. Each one of them will intersect me at least one desired prime. And I know that each desired prime can only show up in one of the Ti. Then I'm done, right? But except, actually, I lied a little bit. So if we were considering elliptic curves, this would exactly be the strategy. But for our case, actually, it's slightly more subtle. So the set T I'm looking here is actually, we will, in our actual proof, this actually will be a smaller T. That there's a little subtlety here. I lied a little bit, but roughly this is the strategy. Okay. Any questions so far?
I'm sorry. Could you explain why? Sorry, why we need condition 3? It seemed
Yes.
like 1 and 2 were enough.
The point is two doesn't work for 5 because at 5 there's only every single curve in a family when reduced by 5 is supersingular. I can't ask it not to be supersingular at 5. That's why I need a different condition to tell apart the reduction of Ci at 5 and the C at 5. Okay, great. Any other questions? Okay, so now this is the SketchUp proof with all the mathematical details being removed, and I hope that's clear. So now let's go to a SketchUp proof with some details. Okay, so first of all, what are my CIs, right? Just like the proof for elliptic curves, the CIs will be CM curves in my family. Okay, so for the SketchUp proof, what I'm going to do is, well, this is more of a rigorous proof now. So what we actually need to do is, given a curve C in my family and a finite set of primes, all we need to do is to be able to construct one supersingular prime that is not in the finite set S, right? That's how to prove there are infinite many primes. Okay, so which means that all I'm going to do here is I need to build one fishing net that catch me one new prime. That's all we're doing. Okay, so now to do this, well, what are the CIs? As I mentioned, this will be the CM curves in my family. So what we do is consider the field Q adjoint square root of 5 and take any positive prime element lambda. Given such a lambda, we will be able to construct a CM curve C lambda. I will explain more details later. But now just bear with me trust me that if you have one such element lambda, which is a totally positive prime element. Oh, just let me just in case it's confusion of any confusion, this field has class number 1. So when I say a positive prime element, well, it corresponds to all the prime ideals. Okay, so given me such element, I can construct a curve that's in my family such that its Jacobian admits CM with some CM field. Then so for the elliptic curve case, we know that we could tell whether a reduction of a CM curve is ordinary or supersingular by a Legendre symbol. Here, we are also able to give such a condition. So moreover, if given a CM curve in my family, I'm able to detect that it admits supersingular reduction at a certain prime P, which is a prime of Q adjoint square root of 5, by a Legendre symbol statement. But one difference here is that for the elliptic curve case, it was if and only if. But actually for the case here, this is only a sufficient condition, but not a necessary condition. Okay, so the point is that if I have this Legendre symbol condition, it implies supersingular reduction, but the converse is not true. Okay, so this is the CM points we constructed, and I know that for these CM points where I get supersingular reduction. Okay. Then we are going to construct a polynomial which has coefficients in Q drawn square root of 5 again, such that if I have a prime P where the valuation, when I plug in J of C to my polynomial and consider its valuation at prime P, if it's positive, then this implies that my curve C is actually isomorphic to a CM point, C lambda mod P. So actually, my polynomial P lambda of X is a monic polynomial given by X minus the CMJ invariance, where J lambda is a CMJ invariant. This again is similar to the polynomials that was used in Alkes proof. But one difference I want to mention is that because our family does not have a cusp, so we don't have a point such that if I have a CM point, I know that it will never reduce to, right? So we know that a CM curve has potentially good reduction everywhere, which means that when I take the reduction, it wouldn't hit the cusp. But here we don't have such a special point. So this means that we were not able to get a polynomial with integral coefficients. Our polynomial will have rational coefficients, which actually impose some difficulty in the proof. And as you can see that when I write out my definition this way, then if a prime P has positive, when I plug in JC to my polynomial, right, and it has positive valuation at P, this means that my J of C equals to J of lambda, so for some J lambda modulo my prime P, which by the definition of my generalized J invariant shows me that my C actually is isomorphic to a CM point after reduced by P. Okay, so with conditions 1 and 2 in hand, now what we need is we need a prime P such that when I consider minus lambda P, this Legendre symbol is not equal to 1, and when I plug in J of C to my P of lambda has positive valuation at my prime P. This is all I need, right? And to achieve that, what we are going to do is also to achieve this Legendre achieve this desired value for my Legendre symbol from a unit, which means that I will be analyzing my P lambda evaluated JC modulo lambda and also its sign. Okay, so the first of all, we're going to start is a reduction of P of lambda evaluated JC modulo lambda. So using deformation theory, as I said, this number will not be integral. It will have numerator and denominator coming from not only just J of C, also the coefficients of P lambda, this polynomial. So we were able to show that the numerator and denominator of this number are squares mod lambda, both of them. And another subtlety is that actually what we will get is might not be this exact statement. Now we might require a change of coordinates. But either way, there will be a similar statement like this one holds. Okay, so this tells me that if I consider J of C minus 27/4, then times P lambda of J of C, consider the Legendre symbol modulo lambda, right? This is the square, which means that this is not -1. This is what we achieve. Okay. And now what I want is I want to achieve something that is a Legendre symbol not being 1, which means that will come from a unit. And in the case of elliptic curves, the unit we had was -1. But in here, we are not going to use -1, but the fundamental unit for Q drawn square root of 5, which we'll see next slide. Okay, but to start a unit, we need to know the sign of P lambda of JC, which means that we need to study where the real roots of this polynomial are. So what we did was we were able to find congruence conditions on lambda, which guarantees that my polynomial P lambda of X having a unique real root. Also, heavy literals holds for both the embeddings of lambda into R. Okay, and then let me continue to explain why we need that. So now the next step we did was to so remember that our goal was to construct a new prime, which means that at a certain time I need to do something to avoid the primes that I already have inside S. Okay, so this is the step we're doing that. So we're going to choose a lambda. We'll show that lambda can be chosen such that the primes about P, if I have a prime P, which is inside S except 5, or if it's a P that shows up in the in JFC minus 27 over 4 to be split, meaning that minus lambda P will be 1 for this P. This means that if later on I construct a minus sign from a Legendre symbol, they wouldn't come from the primes that are already in my set S, or they wouldn't come from the prime that's dividing my JFC minus 27 over 4. And moreover, without loss of generality, let's just assume that 5 is in S. Again, we construct lambda in such a way that my curve C lambda is smooth at 5, just as we mentioned in the sketch. Okay, so what step 5 gave us is some congruence conditions on lambda. Congruence conditions on lambda. Okay, so now let's analyze the real roots of P lambda. So what we did was we actually analyzed some quadratic forms over Q or Jones squared 5, because it turns out that lambda as a prime being represented by a certain quadratic form gives us the location of the real root of P of lambda. So by analyzing certain quadratic forms and how they represent primes, and we were able to locate the real root of P of lambda, and then by applying Hecker's equity diffusion theorem simultaneously for the two embeddings of lambda into R, we were able to obtain the existence of lambda, satisfying all the congruence conditions we imposed before, and also we were able to show the existence. The more important thing is that we were able to show the existence of lambda such that this expression being totally positive. Okay, so why is that important? Because that's the reason is that this part, the part that we already know, JC minus 27 over 4 times P of lambda of JC is a square mod lambda. So we already know from last page that if I consider this Legendre symbol, it is not minus 1. So either 0 or it's 1 because it's square. And moreover, we constructed lambda in such a way that when I plug in the fundamental unit of my Q squared 5, actually it is not a square mod lambda. So I get a minus 1 coming from a 1 plus squared 5 over 2. And moreover, actually for the lambdas we consider, if you use the unit minus 1, actually it doesn't help. So minus 1 lambda in our case is actually 1. Okay, so now with the values of these two Legendre symbols, this shows me that there exists a totally positive prime element, which I'll call it pi p, such that it has positive valuation on P lambda of JC, and its Legendre symbol being not 1, which produces us a supersingular prime of source C that all side of our set S. Okay. So the point is that I know this Legendre symbol is not minus 1. I know this Legendre symbol is minus 1. When I multiply them together, right, I get a Legendre symbol of this expression not being 1, which means that 1 is prime factor is having this Legendre symbol not being 1, and which gives me that I call that prime factor pi p. And then the fact that we have this equal sign also this is a quadratic reciprocity, and it actually also doesn't come for free. This is satisfied because of, again, some congruence condition we put on lambda. Okay. with all the desired congruence condition on lambda, we were able to get quadratic reciprocity and get the desired Legendre symbol not being 1, and which produces us a supersingular prime. Yeah. So that's a sketch proof. Any questions at this point? Okay, so if there are no questions, what I'm going to do next is, as I said, like every step, I'll just add in more details to my proof. So I will add more details to step 1 because I didn't tell you how I constructed these CM curves. I will tell you that, and also I will add in more details of step 4, which shows that inside my CM cycle, I have a unique real point. I'll explain the proof of that. And also I will add in more details for my step 6, which shows the distribution of this set of real points. Okay, so let's start with constructing CM curves in my family. Okay, so taking a curve in my family, this is a genus 4 curve, which means that Jacobian is a 4-dimensional abelian variety. And I know that it already admits Q adjoint zeta 5 in its endomorphism, which is a degree 4 field. So in order to be CM, all I need is a quadratic extension to Q adjoint zeta 5, such that the Jacobian admits CM by then this will give me a CM field. Having a quadratic extension of Q adjoint zeta 5 will give me a desired CM field with a desired degree, which is 8. Okay, so to construct the CM points, first of all, I need the CM field, right? Then I'm going to take the maximal order for my CM field, and I will ask my Jacobian to actually has admits complex multiplication by OB. So this is the CM field. How I do that is, well, so as you can see, as a subfield of Q adjoint zeta 5, this is actually the Q adjoint zeta 5 plus. This is the maximum totally real field subfield of my Q adjoint zeta 5. If I take any lambda in here in F, which is totally positive, and consider the field extension F adjoint square root minus lambda with the quadratic extension, this will give me then, and consider the composition of F adjoint minus square root minus lambda and Q adjoint zeta 5, this will give me a CM field E of degree 8. This is how we construct a CM extension. And when we consider this type of CM points in my family, it turns out that there will be a unique CM type that is compatible with the signature of my unitary Shimura curve. And the CM type we obtained, this unique CM type we got, actually is, as a matter of fact, is primitive, which tells us that the Jacobian of my CM curves will be simple. And then another important thing is I want to know the reduction of the Jacobian of a CM point. Then using Shimura-Taniyama formula, we were able to conclude that by knowing whether a prime is split here, split or inert, or I guess inert or ramified here, it is enough. If it is not split here, at the quadratic extension F to F joint minus square root lambda, it is enough to detect that my CM curve has supersingular reduction at this prime P. So actually, let me just write this is non-split. So a prime that is lies above a prime that's non-split here is enough to deduce that C lambda mod P supersingular. Okay. So as I said, unfortunately, well, not effort. This is just it is what it is. This is only a sufficient condition to show that it is supersingular, but it is not a necessary condition, unlike the Dietrich curve case. So this gives us the Legendre symbol criteria to determine the reduction of a CM point being supersingular. And these are the CM points we're going to start. Okay, so now let's discuss the real CM points given by a lambda. So, well, a real CM point corresponds to a principally polarized abelian variety with CM by OE and isomorphic to its complex conjugate, right? That's what to be real. And then by the theory of complementation, we know that such a principally polarized abelian variety is given by a pair, where you have an ideal class, which is actually the ideal class that's fixed by complex conjugation. So A will equal to A bar, where bar is the complex conjugation, and an element in E which satisfies certain sign conditions coming from the CM type, and this element will induce this element chi will induce a principal polarization for us. And now we want to count such pairs, right? Which means that first of all, we want to study the class number of E, and also we need to essentially study the units, the sign of the units of E. So what we were able to do is by analyzing the number of ramified primes in this quarter extension, we were able to conclude that the class number of E being odd. Okay. And moreover, we were also using the same data. We were also able to conclude that the so-called Hasse unit index, which is given by so E0 is the maximum totally real of E, and the so-called Hasse unit index for E, which is the norm of the unit of E with the index of the square of compared to the square of the units inside E naught, is in this case actually is 2. And this Hasse unit index gives us a bound on the number of principal polarization. And here I want to thank John Voigt for pointing out the reference on the notion of Hasse unit index for us. And using this restriction, we were able to show that we were able to give congruence conditions on lambda, which guarantees the number of ramified primes being a desired number. And this will shows us the number of real CM points in my CM cycle being at most 1. So concretely, what we showed is that if I have the number of ideal classes A satisfying A equals to A bar, at most one has a principal polarization. This is what we showed. We showed that in such CM cycles, the number of real CM points is at most 1. Okay, so this is how we show the uniqueness of my real CM point, which gives me the uniqueness of, so this gives me the uniqueness of my real roots of P lambda of X. Okay. So next slide, I will talk about why do we need this uniqueness and how we're going to use it. Okay, this is related to the distribution. So the point is, okay, so now let's consider my lambda under the 2. So lambda is inside Q adjoint square root of 5. And let me denote the 2 embeddings of lambda on let denote the image of lambda under the 2 real embeddings of Q joint square root of 5 to R as lambda and lambda tau. Then the congruence condition we produced from the previous slide actually guarantees that my polynomial P of lambda and also P of lambda tau both have at most 1 real root. And for those real roots, I'm going to denote it by J lambda and J lambda tau. So in the sketch proof, remember that one thing we needed was for P lambda evaluated at JC times 1 plus or minus square root of 5 over 2 being totally positive, right? So this means what I need is I need P lambda of JC to have different signs under the 2 real embeddings of Q joint square root of 5 to R. And because this polynomial has only 1 real root, whether the valuation at JC is positive or negative only depends on the relative location of my real point, my real root J lambda and JC. So for them to have different signs on the two embeddings just means that I need the JC and the J lambda and J lambda tau to be to be in such a arrangement, right? I need J of C to be lying between J lambda tau and J lambda. Then when I consider JC minus J lambda and JC minus J lambda tau, they will have different signs. These are the two different embeddings of the real part of the JC minus minus J lambda. These are two embeddings of them, right? Okay, so this means that I need to study the distribution of my real roots on my geodesic. So this is where I use the fact that I restricted my J of C to be on the geodesic between Q and R. So what happens is that the real CM points in each of the geodesic correspond to a quadratic form, and corresponding to the prime lambda being representable for a given quadratic form defined over Q drawn square to 5. And the quadratic form corresponding to my geodesic QR is given here. And this is actually a very nice quadratic form. And by analyzing which lambdas are representable by this quadratic form, we are able to give a family of lambdas such that we actually know it satisfies all the desired congruous conditions, and it gives us a unique real root. And then to ask where the real root is, we use Hecker's equidistribution theorem by constructing a ideal character that essentially measures the location of J lambda and J lambda tau. And then we were able to conclude that J lambda and J lambda tau are independently dense on my geodesic. This tells me that I'm able to find one lambda such that J lambda and J lambda tau lies on the two different sides of my GC, which gives us the proof. And that's all I want to talk about. Thank you for your attention.